Welcome to the second video on the definite integral. This is kind of a part two and goes along with the last video. So talking about definite integral, when you hear the word integral, now what I want you to think of is area under the curve. So in this video I want to go over some properties of integrals and understand graphically where those properties come from and why integrals of functions behave the way they do. So first of all, what we said earlier is that if you have a function that's both above and below the x-axis, parts of it are above and parts of it are below, that you could have both kind of a positive area, positive kind of in quotes, and negative area, negative kind of in quotes, because even though area is always positive, the positive and negative really reflect where the area is in relation to the x-axis. Here's just kind of an example, one more problem. I hope by looking at this you'd be able to say that based on what it looks like, or how it looks like I've drawn this. I know I haven't included any scaling, but it looks like if you had the integral from a to b of f of x, whatever f of x is. I haven't actually given you a function here. Oops, don't forget to have a dx on the end. So the integral from a to b of f of x dx. I think we could probably all agree that if you look at this graph, it seems like the area, the total area, or sometimes we call that the net area, is going to be negative because there is more area, or at least it looks like it, that there is more area down below the x-axis than there is above. And so some of this positive area over here is going to kind of cancel out some of the negative area that's down here, but it definitely looks like there's more negative area than positive. So it makes sense that when you add the positive area together with the negative area, there's more negative area, you get a negative as a whole. So there's some interesting results we get from this, and so just want to look at a couple of the properties. First of all, you might ask about functions. We talked earlier about when does a function have a derivative. You might ask natural questions like, how do you know when a function is able to be integrated? Or the word we would use for that is, when is a function integrable, which is a weird word to say. But how do you know whether a function is integrable? And so here's kind of an important result, is that a function is integrable, so is able to be integrated is kind of what that means. So integrable, there we go. If f has a finite number, or that could be none, by the way. Finite number could be 0. A finite number of what we're going to call jump discontinuities. And to kind of start to look at some of the properties, we're going to start to look at some of the properties of functions and see how what having discontinuities could possibly affect being integrable or not. So here's a function. I know it's going to be a little small because my words are taking up a lot of the page, but here's a function that kind of goes all the way up here, and then it kind of stops, and it has what we would call a jump discontinuity. If you remember back with continuity, way back earlier in this class, a jump discontinuity says that basically you kind of have this jump from one to another. And so let's say A is right here and B is right here, and you might ask, can I find the area under this graph from A to B? And there's this like weird jump right here. But if you think about splitting this up, where you have another value right here, I don't know, I guess we'll call that C, you could find the integral from A to C, which would be finding the area there under that graph. And you could find the integral of f of x dx. You could find the integral of f of x dx from C to B as well, and you could find the area of that shaded region also. And you could just do these separately. You could find one area and then the other area, and if you think about what's the total area under that whole kind of shaded region, it comes from adding the two different sub areas there together. So if you have a bunch of these little jump discontinuities, you can kind of break up your function as being the shaded area between jump discontinuities. and get a spot where this value of c here doesn't really mess anything up too badly, because when we're looking at the area under the curve, so it's kind of surprising, we actually only really care about the open interval from A to C and the open interval from B to C. So when people think that that value of C is going to really mess things up, but it actually doesn't really do anything too crazy when we're talking about being integrable. So it brings up a couple of different results. Let's say you're talking about the integral from A to C of a function, and let's say that B is somewhere between A and C. So I want you to think about kind of what this means on a graph. Let's say that you have a graph over here, again, going to be pretty small, but like you have A, you have C, and you have a value B that's somewhere in between. And you want to know about the area from A to C under the graph. Remember, integration just means the area under the curve. And so if you look at the area from A to B of f of x dx, and you add that area from A to B with the area from B to C, that should just give you the area from A to C. And so it kind of works that you can split up a bigger area, a bigger region, into two smaller areas, and work with those two smaller areas separately. Okay, so there are some other kind of, I would say, smaller rules that also work the same way you would think they do. Some rules that work the same way as with derivatives. So, for example, let's say you're integrating from A to B, and you have some constant that we'll call C, I guess. It's pretty standard. So C times f of x. So C this time is not an x value as a bound. C is just some constant. If it is easier for you, because we just use C, if it's easier to call it K for a constant that's spelled incorrectly, that's fine. We could do that as well. So you can think about what would you expect to happen when you have some constant K. It actually works exactly the same way as when you're taking derivatives, is that you can just kind of leave that constant multiplier out front and then look at the integral from A to B of f of x dx separately. This is kind of like saying take the derivative of a function and then just multiply by that constant multiplier that was out front in the first place. Okay. Let's see, other ideas here. This is a little bit weird, but if you're talking about the integral from A to B, and if you think about flipping your interval around and instead going from B to A, you're kind of going in the reverse order. These are actually related to each other, but they're related to each other in the sense that when you flip the order of your interval, like if B is bigger than A, then it makes sense to go from A to B, but if you go from B to A, you're kind of going backwards. You actually get the opposite integral. You actually get the opposite value of what you would have. So there are just different ways that integrals kind of work together here, and we'll see some examples in the next video about how some of these properties of integrals work together and kind of give us some nice results. Now there's a couple others that I think make a little more sense when we think about visually, kind of visualizing what a function looks like. And so here, these are all listed out in our book, by the way, and you can kind of see these in. If you go take a look at the book, in a next video, I'll actually pull up kind of a page that shows you all of these different rules, all of these different properties. But here's a couple others that when you think about an integral as being the area under the curve, hopefully this kind of makes sense. So here's one that, another one that we could look at. It says if f of x is greater than or equal to 0 for a is less than or equal to x is less than or equal to b. So I want you to think about kind of what does this mean for a second. So this means that you have an interval starting at a, ending at b, and x is some value in between those. Okay, and so x is your variable here, but you're using an input of f of x that is between a and b. And so keep in mind that this is saying that if f of x is greater than or equal to 0, so that means it could be above the x-axis the whole time. It means it could come down and actually touch the x-axis, but it can't be less than the x-axis. You can think about what should happen when we're talking about the integral from a to b of f of x dx. Go ahead and think about that for a second. What do you think should happen to the integral from a to b of f of x dx if you know that x has to be between a and b there? If you said that the integral from a to b of f of x dx has to be greater than or equal to 0, you're right, that's true. Okay. Now, you might say, well, why is it greater than or equal to 0? Why not just greater than 0? Well, think about this example. What if you have a situation where a and b and you just have this straight horizontal line, like let me use a different color, let me use blue here. You just have this straight horizontal line on the x-axis from a to b. Remember, thinking about the area under the graph, or think about the integral, is supposed to be the width times the height of each rectangle, or the base times the height. Well, if you drew little rectangles in here, they wouldn't really be rectangles because they wouldn't have any height. They would have a little bit of a width somewhere in there, but they wouldn't have any height. So basically, this integral could also equal 0. So that's another one to keep in mind. Other ones look very similar to that. So here's another one. So this is not comparing a function to 0. Now we could look at this and say, what happens if f of x is greater than or equal to g of x? And this is going to almost feel really, really similar to the last one. In fact, this should hopefully maybe even remind you of some stuff from your past about how different things relate to each other. I'll just give you a little bit of a hint. Do you remember seeing one thing is less than another somewhere in our past? My hope, and that would be great, my hope is that makes you think of the squeeze theorem way back in the day about how if one thing is less than another, what's going to happen with the limits. Okay, I know it's been a while, but let's see, if f of x is greater than or equal to g of x, and x is between a and b, again, think about what's happening here. Here's a, here's b. What can you tell me about, let's say you have a function f that is always bigger than g, or at least bigger than g on that interval. What can you tell me about the integral from a to b of f of x dx and the integral from a to b of g of x dx? Go ahead and think about that for a second with this picture. What should happen to the areas under those curves? So in blue, that is the integral from a to b of g of x. I'll put the other one in green here. In green is the integral of f of x dx from a to b. Hopefully what you should have come up with is that the integral from a to b of f of x dx had better be greater than, because of this or equal to right there, it also could be or equal to the integral from a to b of g of x dx also. If they're exactly the same function, at least on that interval, then they could have exactly the same integral. But if f of x is always greater than or equal, it is not possible for the integral from a to b of f of x to be less than the integral from a to b of g of x. Okay, so there is one more result that we're going to take a look at when we look at the next section, where we're going to have a pretty good-sized proof for one of the most important results that we're going to be looking at this semester. It is called the fundamental theorem of calculus. It is incredibly important and powerful and useful. But there's one more result that we're going to look at with integrals that helps us be able to prove that. Okay. Check the next couple of videos for some examples for using some of these rules with integrals.